Oh, I couldn't have gotten here without the work of many, many colleagues. And there's a half a dozen of them in this room that aren't on the list that should be. So I'm going to switch the list quickly. But I owe a lot to all of my colleagues here in the Pacific Northwest and around who have helped me understand a little bit about how the Pacific Northwest works. My dad was from Hood River, but I grew up on the East Coast. And I always thought of the Pacific Northwest as kind of a Garden of Eden on an apple crate. And, just this idyllic, beautiful, snow-capped peaks just sitting there doing nothing. And, but today, Cascadia really, we have a completely different picture of Cascadia. And, I've spent at least the last 20 years, quite a few more than that actually, trying to understand what's going on here. The eruption of Mount St. Helens and Brian Atwater and his colleagues' studies of the subduction zone and its past history of great earthquakes have changed everything. The center there is, my version of Steinberg's famous New Yorker cover, with the addition of the Great Pacific Northwest Tsunami. On the right, of course, is, Catherine Schultz's paper on the really big one, which really shook up the Pacific Northwest in a different way. But in fact, trying to understand, how what we see on the ground is related to the GPS velocity field, the subduction zone seismic cycle, and the sweep of magnetism across the Pacific Northwest is, to me, a really interesting and sometimes overwhelming problem. One of the spectacular data sets, of course, that we have in the Pacific Northwest is this GPS velocity field, which is remarkable. Here from McCaffrey and others. It reveals this beautiful pattern of clockwise rotation right here, and also a eastward push from the subduction zone here. You can see the arrows get shorter as you go inland. And one of the sort of critical questions to me is how this rotation manifests itself in the crust. How is crustal deformation related to this, if it is, and earthquake distributions? How does this affect the Cascadia magmatic arc? And how does it affect the megathrust? So those are some questions that I kind of want to address in this talk. And I'm going to start off with some prehistory. That means pre-plate tectonic paleomagnetic studies, which early on revealed the clockwise rotation in the Pacific Northwest. Then I'm going to go back to that GPS data and look at how Rob McCaffrey and his colleagues have interpreted it in terms of block subduction zone and rotating blocks. And then look at how those block rotations drive upper plate earthquakes and faulting, modulate the megathrust behavior, cause migration. And if we don't run out of time, maybe discuss a little bit about how it might relate to mantle flow underneath everything. Although I'm not sure I understand that myself. So we're going to start with paleomagnetism and how it reveals clockwise rotation in the Pacific Northwest. Now, in 1957, Alan Cox reported unexpected easterly directions for the 50-million-year-old Siletz River volcanics. And in that, his magnetic directions were east of north. This is a stereo net. We're looking at the lower hemisphere. North is up here, east is over here, straight down is in the middle. And just to remind you, the sort of expected magnetic directions, one would assume from a series of lava flows sampling a significant period of time, they ought to basically point north for the time period that they represent. And of course, the magnetic field is inclined to the surface of the Earth. At the equator, it's horizontal. At the pole, it's vertical. And so the direction is latitude dependent. So here we have the expected magnetic direction for today in the Oregon Coast Range. It has an inclination of about 65 degrees and a declination of 0, points toward the north. Here are the 8 flows that Alan Cox sampled. The black dots represent normal polarities, and the white dots represent reverse polarities that would plot in the upper hemisphere over here, but they've been inverted through the center of the stereo net so that you can compare them with the normal polarities. But the important part is that they're 70 degrees east of the present day expected field. And in 1957, they didn't really know what this meant. In fact, it happened to coincide with the magnetic pole from the Deccan traps in India, which confused a lot of people. However, not too long after that, Ted Irving in a textbook, 1964, proposed that the easterly declinations was the result of oroclinal bending of the Cordillera in a dextral shear couple between the San Andreas Fault and perhaps the Rocky Mountain Trench. But in that, this big oroclinal bend actually produced that eastward deflection of the paleomagnetic directions. So problem solved. Why do we care anymore? Well, 8 measly flows. Are you going to hang the entire Cordilleran orogenic history on 8 flows? Probably not. Alan Cox and others went back with Bob Simpson to study the Siletz River volcanics again, the Eocene oceanic basalts. And so did a lot of other people. So between 1973 and 1990, we sampled over 10,000 cores at 1,500 sites in the Pacific Northwest, somewhere between 30 and 50 individual paleomagnetic studies. And in fact, the pattern holds. The Siletz River volcanics are right here with 70 degrees clockwise rotation. Siletz River volcanics in Roseburg have 79 clockwise rotation. And successively younger flows, packages have less rotation. But this area in the Oregon coast and up into the southern Washington coast range is rotated the most, whereas same age rocks in the east are rotated less, in the south they're rotated less, and in the north they're rotated less. So that all kind of potentially fits with some sort of large-scale tectonic deformation. Oops. So the early paleomagnetists, this is work we did with Jim McGill and Alan Cox at Stanford, Bob Simpson and I, favored microplate rotation type models. One, they avoided the fact that we didn't know much about the local geology in detail, and that was handy, and the fact that it was completely covered by trees. So so thinking about it in terms of big rotating microplates seemed useful. And this, for example, is looking at paleomagnetic data from the Pomona flow, which flowed about 700 kilometers 12 million years ago in the Columbia River Basalt Group to the ocean. And the ocean declinations are pointing further east than the declinations from the more stable part of the continent in the interior. Here you can see it in profile view. This is east, this is west. Here's the Cascade Range, and this is the deflection of the declination. Here are the plateau averages. Here are the Coast Range averages. It's about 16 degrees of clockwise rotation in 12 million years. And so they liked, we thought, well, let's pick a pole that does the least damage, and we put a pin in it right here and rotated it clockwise with the opening of the basin or range to produce the tectonic rotation. There's no real northward transport in this sort of model because it's pinned right here. Well, there were good reasons for thinking that there might be a microplate-like body in Western Oregon. First of all, it's relatively aseismic. There's lots of earthquakes to the south, lots of earthquakes to the north. And on its eastern edge, that's where there's the volcanic production rate is the highest. And the paleomagnetic rotation, of course, is large here and small to the north and south. And so basically, we can divide up this margin into sort of a northern compressional arc, which is seismically active, low extrusion rate, lower heat flow, folded basement, small forearc rotation, from a central extensional arc, which has relatively low seismicity, but high extrusion rates, an axial graben, and large forearc rotations. And the southern part has lower rotation, although it is seismically active and has high extrusion rate as you get down near the triple junction. So the seismicity, the volcanoes, and the earthquakes all define a potential Oregon forearc microplate, here labeled OC for Oregon Coastal Block. So what can we do with this paleomagnetic data? Well, if we use plate tectonic theory, we can calculate the velocity of the Oregon coastal microplate with respect to North America. That's these red arrows here. If we know its rotation rate from the paleomag, and we know something else about something attached to it, like the Sierra Nevada block here to the south. Well, Argus and Gordon in 1991 published a pole of rotation, an Euler pole, for the motion of the Sierra Nevada block, presently based on very long baseline interferometry, which was sort of a precursor way from GPS to try and determine the motion of the crust on the surface of the Earth in present day. So if you have a pole of rotation for the Sierra Nevada block, you can add the Sierra Nevada block with respect to North America to the Oregon Coast Range with respect to the Sierra Nevada block, knowing that the Sierra Nevada block hasn't rotated very much. Then you can calculate a pole of rotation right here for the Oregon coast with respect to North America. And these red arrows represent the velocities that you can calculate from that pole of rotation. So the northern part of the Oregon block is moving northward at 6 to 8 millimeters a year toward relatively stable Canada. And as I say, squeezing the soft underbelly of Washington as it goes. And the interesting thing about this model is that it doesn't use GPS, right? We're using the motion of the Sierra Nevada block to predict the motion of the forearc in Oregon. And this model, the motions of the blocks here, match the basin and range spreading rate calculated from other data. 5 plus 4 plus 1 is 10, which is about the length of this arrow right here. It matches the northward change from extension in the southern arc to compression in the northern arc. And it also explains the north-south shortening in the forearc along the Seattle thrust fault and other east-west thrust faults like the Yakima fold belt in Washington. So this is a long-term motion. There's no locked megathrust in this story. The megathrust is missing in action here. We're not talking about it yet. And so it's useful for understanding upper plate faults and volcanism. Now, when you get back to the GPS velocity field, right, we have not only that clockwise rotation, but we also have the eastward shortening or of the vectors here along the coast. The coast vectors are much longer than the interior vectors pointing to the east. So how do we separate these two components, the rotation and the subduction signal? Well, Rob has a program called DefNode, Rob McCaffrey, who was a research associate here at Portland State after he retired from RPI. And we can divide this thing up into fault-bounded blocks based on the distribution of earthquakes and known or perceived potentially active faults, and solve for the block rotation of each block and the locking on all of the stuck faults. Of course, the biggest stuck fault is the subduction zone megathrust offshore, which is the boundary between the forearc blocks and the Juan de Fuca plate. And so we did this for 16 different models, trying all of the various combinations starting with a 2-block model, Juan de Fuca, North America, Juan de Fuca, 1 rotating block, Juan de Fuca, 6 rotating blocks, Juan de Fuca, 11 rotating blocks. And the statistical improvement of the fit to the GPS improves as you make the blocks smaller and smaller. But then if you get them too small, then the uncertainties within a block blows up because there's so few GPS sites in it. So the best sort of fit model here is shows the different blocks and their boundaries in the Pacific Northwest and their clockwise rotation about their various Euler poles here in the back arc. This is the one for the Oregon 4 block, rotating about 1 degree per million years, which is pretty close to the Paleomagnetic rate. And what it shows here from, say, Portland, Astoria area, up into Canada is about 7 or 8 millimeters a year of shortening across that distance. And that conceivably could be driving these block boundary faults in that area and causing shortening. But in addition to that, you can solve for the locking on the subduction zone, which is the picture on the right, where the red is fully locked and blue is fully uncoupled. And it suggests that there's a patch, a large area on the subduction zone interface, which is locked and loading up for the next great earthquake. So how do these two models, or how do this GPS-derived model and the plate motion model derived from Paleomag and far field VLBI data relate? Well, fundamentally, this would be the GPS vector. The GPS velocity is fundamentally the secular plate motion from plate tectonics plus the eastward push from the locked subduction zone. So basically, this GPS velocity field is the sum of this, basically a model like this, plus the shortening from the subduction zone. And one of the interesting things about this is that this velocity here of 8 to 6 millimeters a year from the plate model matches pretty nice with the GPS interpreted velocity of shortening across that region of 7 to 8 millimeters a year from the GPS data, which suggests that these two models might be telling us something similar and about the way the margin works. So how do these block motions drive crustal faults and earthquakes? What do the rocks tell us? Well, if you go out and look at them, you see a lot of cool stuff. And the forearc rocks are deformed. And if it wasn't for, Kronzellerbach and Weyerhaeuser and all of that, we'd have no idea what's going on out there. But I happened to be mapping during the maximum time of road building in the Coast Range. And there were lots of exposures of bedrock along logging roads and in borrow pits. And this is an example of some horizontal slicken lines on a left lateral fault in the Coast Range and some fault breccia and gouge plastered into the side of it here. Here are horizontal slicken lines from fault plane near the Gills Creek fault system, just west of Portland. We mapped hundreds of fault slip data from hundreds of faults in the coast ranges of Oregon and Washington. In addition, I followed the paleoseismologists around and would jump in the trenches whenever I could to measure the fault slip data in the trenches for Quaternary and Holocene fault slip exposed in these trenches. And with that kind of data, you can plot them all together for a particular fault or fault system. You can plot the data together. And what we're after is whether or not we can see this north-south shortening of the forearc. We can also see evidence for small block rotation, but I thought I didn't have enough time to talk about it. It's tacked onto the end in case we do have time. So let's look at what kind of data we get. So we can add fault slip data. For example, here's stuff that Scott Bennett and I collected from the Gills Creek fault system, which is a right lateral fault oriented about like this. And there are a bunch of conjugate or smaller step over structures oriented like this with left lateral slip. These have right lateral slip. And when you combine them all in Allmendinger's program, you can come up with something that looks like a focal mechanism, which summarizes the slip on all those faults in this resulting beach ball here. And so it's analogous to a focal mechanism, and it is, for example, here, what a basic strike slip focal mechanism would look like. And here's what it looks like when you add a bunch of faults from a strike slip system and calculate a composite fault plane solution. So we've done that for many different places in the Coast Range. First, we'll look up in the Willapa Hills of Southwest Washington, and then we'll look down here in sort of the Tillamook Bay area. Now, we've done this for faults that go back 50 million years. We have 50 million years of fault slip, but we're going to just focus on the last 16 million post-Columbia River basalt time now and look at the faults that deform Columbia River basalt and get a picture for what the Neogene or late Cenozoic deformation looks like in the Coast Range. So first we'll look up here in the Willapa Hills. This is all the Columbia River basalt here. And here, all of this data is data we're not going to talk about from the accreted Siletz terrain. And what we're focusing on is the red dots, which are faults that cut and deform Columbia River basalt. And in fact, these are the slip vectors that the composite focal mechanisms that we get from the Doty fault up here, which is a thrust fault where Columbia River basalt is practically vertical on the north limb of a syncline. Here's the south limb where it's dipping north about 10 degrees. Here's another syncline going down the Columbia River. The Columbia River basalt here is almost vertical in places along the north limb. South limb's dipping north about 10 degrees toward the axis incline. So we have Yakima fold belt-like structures actually in the forearc taking up this north-south shortening. And we can see, so what kind of focal mechanism is this?
Oblique.
Oblique what? Is this a normal fault or a thrust?
Thrust.
Yes. Good. You get a beer. Right. Here's a right lateral strike slip fault. Here's an oblique right lateral thrust. So basically, we're taking up this north-south shortening that Oregon is putting the squeeze on Washington, right? And the rocks are telling us that. Here are some Columbia River basalt fault systems in the Tillamook Bay area. Again, we have north-south maximum horizontal compressive stress, we have right lateral faulting, and we have north-northeast shortening along the coast. So let's look at the Quaternary structures from some of the deformed rocks along the coast and from fault slip in paleoseismic trenches. First, we'll look down here along the Tillamook coast. And here we're looking east at a sea cliff with a fluvial channel coming out at us. And it's filled up with gravels and sands and paleosols up to a capping paleosol up here at the top. This is a breached anticline. This is Columbia River basalt dipping vertically to the south. And here's Columbia River basalt dipping to the north. And these are thrust faults cutting through that anticline and offsetting the wall of this Pleistocene channel. And the slip direction from them is also in the Quaternary. We don't know the age of the fill. It's older than 50,000 years, radiocarbon. So could be as old as 100,000 years. I'm not sure yet. We still have more work to do. But there again, we have thrusting. If we go up to Washington, we have a lot of data around Puget Sound and around the Olympics. And here along the south side of the Olympic, it's really cool. There are big reverse faults, which bring the Siletz Eocene basalt of the Crescent Formation, the Siletz terrain, up over Holocene soils. And in fact, if you look at that fault plane right there, the slip of the hanging wall is up and to the left. It has a left lateral component to it. Here's another one just to the northeast, where the slip again of the hanging wall is up and to the left. And so we're in fact looking at left lateral reverse slip along the south side of the Olympics. And other paleoseismic data has suggested right lateral along the Devil's Mountain Fault, and new data suggests right lateral along the Leech River Fault. But we've actually looked at some of the faults along the Boundary Creek Fault Zone on the north side of the Olympics. And in fact, if you put together all of the fault slip data from the Seattle Fault, the Seattle Fault is right here. And from around the Olympics, here are the beach balls showing left lateral slip along these fault plains, along the south side of the Olympics, along the Seattle Fault right here. It's all thrust slip in the Holocene. And on the north side of the Olympics, it's right lateral slip. So in fact, you're documenting that north-south shortening in the forearc. And in fact, it looks like the Olympics are trying to escape westward out over the trench. But there's something holding it in over here, perhaps. And so that westward escape may actually help contribute to the uplift in the Olympics. So let's look at how all of these fault plane solutions compare to modern earthquake focal mechanisms. So I showed you the Neogene fault slip from the Columbia River basalt down here, showing north-south shortening and strike slip faulting. I showed you the Quaternary from down here in Oregon, again, northward motion, northward shortening. And then I just showed you all the Holocene here, again, northward motion and westward escape of the Olympics. And these three look just like these three almost. It's quite remarkable. And these are earthquake focal mechanisms over the last 20 years or so. And so the bottom line is that Holocene, Pleistocene, and post-16 million year fault plane solutions match today's earthquake focal mechanisms. And means to me that the north-south shortening observed in GPS data has persisted for millions of years, as suggested by the microplate models. So what happens if we look at the megathrust? So we have all these faults. And they are cutting across the forearc. How do they affect the megathrust, which underlies them and is offshore? And of course, this purple stuff here, this is Rick Blakely's contour map from a paper on episodic tremor and slip and its relationship to crustal faults in the forearc. So this is the density of tremor along the megathrust between 30 and 40 kilometers depth, down below the lock zone, where the plate boundary is intermittently slipping, like a squeaking door. So, and the interesting thing about it is where the faults cross the forearc and cross the tremor at depth, the tremor seems to be muted somehow. Tremor lows underlie crustal faults that bound the northward migrating forearc blocks. So why is that? Well, this over here just shows you statistically that the tremor near faults in red is quite different in its distribution, tremor density distribution, than tremor far from faults. Tremor near from faults has higher densities than, has lower densities than tremor far from faults. So in fact, it's statistically very unlikely that the near fault distributions are a random sample of the tremor population. So tremor on top of faults, tremor underneath overlying faults is lower. And the question is why? Well, Our interpretation is that the faults provide pathways for fluid escape. Where the tremor is occurring, people have argued that it's occurring because the fault is overpressured with fluids, and that is a requirement for the production of tremor. So if you have a fault, and let's say these faults go all the way down to the megathrust, if they go all the way down to the megathrust, they could provide pathways for fluid to escape from the megathrust. And if fluids can escape from the megathrust, then perhaps there'll be less tremor at that location because fluids are needed to produce tremor. So here's a view, for example, looking east down the megathrust right here. Here are the earthquakes in the upper plate. They go down to 35 kilometers in the upper plate. Here are projections of the fault plains in here projected essentially vertically, although some of these faults may not in fact be vertical at great depths. We don't really know. Some of them are certainly reverse or potentially thrust faults near the surface, but these faults have fairly straight orientations, suggest fairly steep dips. And in fact, these would be good paths for fluid migration off the megathrust. And so fluid transfer between faults may be an important process linking megathrust segmentation and upper plate behavior. And if those fluids are actually coming up into upper plate faults, they're charging upper plate faults. So it turns out there is an inverse relationship between upper plate earthquakes and tremor. So I don't have a slide of that, but that's a very interesting relationship in Cascadia and elsewhere, also in Nankai, Southwest Japan. So fundamentally, it's the water. As the Olympia beer was way ahead of its time. Kind of miss it. So what do these upper plate faults do offshore? Well, they project into some interesting gaps in what is interpreted from coastal subsidence as possible patches of slip during the 1700 earthquake. And that's kind of interesting, although there are other ways to map the slip on the earthquake. Then you might be able to make those gaps disappear to some degree, but there is variable subsidence along the coast, which suggests something variable going on the interplate, on the interface between along the megathrust. So what do we see in those places? Well, the work of McCrory and others off of Grays Harbor, there are all of these folds and faults which run east-west. They appear to be taking up north-south shortening. The same thing here in Willapa Bay from McNeil and others, and in the Halem Bank, where the faults actually curve from taking up north-south shortening around to taking up east-west shortening out here. Now, I had a version of this where I showed the anticlines offshore along the fold and thrust belt, just inboard of the deformation front. Those, of course, are all parallel to the plate boundary, and you can see the folds here. So out here, the shortening is east-west, whereas inboard near the coast offshore, immediately offshore, it appears that here's the Cape Blanco anticline of Kelsey and others, where coastal terraces are deformed into an anticline that runs east-west. So it suggests that this north-south shortening does have some effect offshore. Exactly what it might be, we're not 100% sure. And this is an area that a lot of people are interested in working on and are working on it now. So what happens to the arc? Well, the block motions produce a migrating magmatic arc. Over time, the Cascade forearc has been rotating clockwise, and the arc has been trying to keep up with it. So let's look at that. On the left here, we have sort of a geologic map of the volcanic rocks of the Cascade Arc. Again, we can see the tremendous volume in Oregon compared to how little volume there is up in Washington and British Columbia, northern Washington and British Columbia. The oldest part of the arc is on the west out here. And then progressively eastward, it becomes younger and younger until where the modern arc is, the rocks are the youngest. And so this is a really interesting pattern here. And it's been a puzzle for a long time. One possibility of interpreting this is that in Oregon, over time, the slab has been shallowing, so the depth of the magma production moves eastward. That's a possibility. But here in this simplified picture, here's the active arc in green, and here's the Miocene arc from the Pluton orientations, trends in red. So the Miocene arc is west of the active arc in Oregon, and in British Columbia, it's east of the active arc. So if the slab is shallowing in Oregon, it would have to be steepening in British Columbia. This would be going from here to here in Oregon and from here to here in British Columbia. So one possibility is the slab is doing this. The other possibility that I prefer is that steady clockwise rotation of the upper plate progressively offsets the arc. And so here we have plotted, these are the GPS derived velocities from the McCaffrey et al. Plate motion model. Here's the Oregon 4-arc pole at a degree per million years. Here are these red lines, which are the velocity of the Oregon 4-arc. And in fact, you can see that where the Oregon 4-arc is moving to the northwest, the Miocene arc is offset to the west. Up here in the Vancouver Island block, the velocities are to the east, and the Miocene arc is offset to the east. So the simplest explanation here is that the old arc rotates clockwise away from a magma source region, which is not moving as fast. And the inference is that we can use these GPS-derived block motions. We're going backwards now. Instead of taking the paleomag and the stuff going forwards to understand today, we're going to take today and go backwards to understand the geology using GPS. We can use them to interpret the late Cenozoic arc history. So if we go up here to Mount Baker, right there, for example, here's Mount Baker. And as we go to the northeast, the successive volcanic centers become become older and older. Colchen's 1.1 million, Lake Anstock is 2.8, Hagman Caldera is 3.7. This is the work of Hildreth and others. And in fact, that orientation is in the direction of the Vancouver Island block motion at 3.5 millimeters a year. But the progression of volcanism is at 6 millimeters a year. So what might be going on here? Well, we think the block is moving to the northeast, but we think the slab is rolling back toward the ocean at 2.5 millimeters a year. And so if you add those two together, you can explain the magmatic progression with a combination of block motion and slab rollback. That's slab rollback with respect to North America. And down south, down here, it's a little bit different in the sense that the GPS predicted location of the Miocene magmatic arc is further away. The magmatic arc is not as far as the block motion would indicate. So you have nearly 8 kilometers per million years motion of the Oregon block, but the arc source is only moving at 4.2 millimeters per year. That suggests that that there's 4.2 kilometers per million years of slab rollback here in order to try to keep up with the trailing edge of that rotating block. The trailing edge of the rotating block is going to be a big crack, right? It's going to be a big extensional area. And in fact, that's a good place for magma to come to the surface. So the point here is that the active arc in this model has occupied the trailing edge of the rotating block since 16 million years. Here we are at 16 million. Here we are at with the trailing edge at 10 million. Here's the trailing edge at 5 million. Of course, today the trailing edge at 0, which is not shown, but the dark green would be right in the middle here. So that motion is moving at 8 millimeters a year or something like that. And in the back arc, we have this beautiful progression of rhyolite ages, which become younger and younger toward the modern arc, from about 10 million years to about 0. And I think that's right here. And it looks like it's moving faster, and then it slows down later in the picture here. But this westward migration of arc magmatism, I always thought it was moving at the rate at which the block is rotating, but it's not. It's moving much faster. The block is rotating at, I don't know, 8 or 9 millimeters a year or whatever, maybe 10 down the south. But the magmatic production rate across there, the migration rate of these rhyolites is on the order of 33 millimeters a year, between 10 and 5 million years. So there's something else going on in the back arc that's producing this migration to the west. It's sort of the anti-hotspot trend. Okay, it's going in the opposite direction from Yellowstone. But what's interesting is that when it gets close to the arc, it slows down. And that suggests to me, the fast rate suggests that the subduction rate suggests that mantle corner flow, the only thing that's moving that fast is subduction, right? The plate going down is going down at 40 millimeters a year. So if it's making the mantle do this, then this flow back toward the arc could conceivably be going relatively fast in this picture. And Swenton and others have described this as pulsing with magma pulses between 12 to 9.6 million and 8 to 5, and then slower after 5. So this could be somewhat episodic, but it is something else going on besides the rotation of the block. I hate to show this slide because it's kind of complicated, but let's look at a cross section through this and think about what might be happening, or let's just get a kinematic feel for it. Let's assume that Yellowstone is fixed in the hotspot reference frame and everything is moving with respect to Yellowstone. So North America, so first of all, the arc over here is getting younger in this direction from 16 to 0. The high lava plains is getting younger in this direction from 10 to 0. The high lava plain migration rate is 33 millimeters a year with respect to North America. And North America is moving at 26 millimeters a year with respect to a fixed hotspot. So high lava plain with respect to the hotspots going almost 6 centimeters a year westward. One of the possible sources that people have described for the high lava plains is sucking up some plume and driving it westward with the corner flow. Others suggest hot subslab mantle or some other asthenospheric thing might have something to do with it. There may be other explanations, but fundamentally, North America is moving 26 millimeters a year westward. Slab rollback based on the relationship, the progression of volcanoes is on the order of 30 millimeters a year with respect to the hotspot. And the forearc is going 7.7 kilometers per million years with respect to North America. So that would be 33 millimeters a year with respect to hotspot. So the rotating forearc is moving, the decreasing age of these arc volcanics on the trailing edge of the rotating block means that slab rollback is not quite keeping up with the speed at which the block is rotating. And that suggests that the motion of the block is because of that Sierra Nevada push from the south, all right? That it's actually a lateral transmission of stress force instead of underlying mantle motions. And the high lava plain progression is 9 times faster than slab rollback with respect to North America, suggesting we need this corner flow to perhaps help produce the high lava plains. And Maureen Long in 2016 wrote a cool paper trying to look at the stretching and olivine in the mantle, which shows the direction of motion of the mantle at depth. And these long directions represent the fast direction of seismic waves in the mantle underneath the lithosphere. And here at 100 kilometers depth, the shear wave splitting shows some complicated relationships in the Pacific Northwest. And some of the original work suggested that the clockwise rotation that we see in the upper plate had no obvious relationship to the shear wave splitting underneath, suggesting there wasn't a relationship between the way the blocks were rotating and the way the mantle was going, right? But if you open your aperture a little bit, you can see that if this direction is related to Juan de Fuca subduction, and this direction is related to Pacific, and this direction is related to the deep structure of North America here in the cold, thick part of the North America lithosphere, and this direction could be the result of the rollback, the return of Juan de Fuca mantle flow above. You do get a gross clockwise rotation, but it requires looking at all of the three plates involved to see that. When you zoom in close to one of these velocities, it doesn't necessarily match up with the mantle flow direction, which is consistent with the idea that it might be driven by end forces related to block motions interacting with one another. So to summarize, paleomagnetism, GPS, potential fields, LIDAR, geologic mapping have revealed active crustal structures that accommodate rotation at a variety of scales, from microplates to crustal dominoes, which we didn't discuss. Clockwise rotation is a major driver of crustal faulting, migration of magmatic systems, and possible seismic segmentation of the megathrust, and it's a manifestation of the broader Pacific North America shear. The Oregon Fork block rotation is faster than arc migration and implies push from the Sierra Nevada and possibly strong blocks. The rotation may be broadly reflected in the underlying mantle flow. And if I had some questions that are unresolved, just exactly what happens offshore with the megathrust is a subject of great interest, and a lot of people are working on it. How it relates to seismic segmentation, the location of high frequency sub-events, which are places where strong ground shaking might come from, and how it relates to the slow slip events at depth is really important. A recent paper by Walton, Steisch et al. In 2021 gives you a pretty good overview of what the current understanding of the megathrust is. One of the things about the GPS velocities is that you don't see right lateral shear and arc stretching in the GPS data. And you see lots of right lateral faults in the geology, and you see lots of graben faults in Oregon, but you don't see it in the GPS. And the question is why? Is it because it's where we are in the subduction seismic cycle, or is there some modeling glitch or whatever? And then finally, rotation versus mantle flow. Resolving this has implications for plate driving force and strength of the crust. Okay, thanks.